So the exponential growth curve is a little unrealistic because it doesn't take into account the fact that the populations can't grow exponentially forever. So the logistic growth curve is a more realistic model that's going to take into account something called carrying capacity. So the carrying capacity, which is going to have the variable k, for those of you who are playing along with the math equations, this is the maximum size that the environment can support. Remember that we have populations that live in some kind of habitat. So within a habitat, you can't have infinite number of individuals. Density has a maximum. So the carrying capacity puts a limit on the number of individuals that can live in any potential habitat. And this is determined by limiting resources. So if you're a plant, this might be access to sunlight, it might be nutrients, it might be access to water. If you're an animal, it might be access to prey or plants. A lot of times these resources are going to be things like food, water, nutrients, things that organisms themselves need to grow. So this logistic growth curve is going to start looking pretty similar to the exponential growth curve. And then eventually, once this population starts to reach this carrying capacity, this curve is going to look a little different. So here you can see both of these. The logistic growth curve is shaped like an S. So logistic has an S in it. This is an S. I don't have a one for exponential. Exponential is a J. So here we can see that this is two models of the same population here, and they both have the same growth rate, so 1 and 1. Only this one has some extra math on this model, and that's because it's taking into account that the carrying capacity is 1,500 individuals. So this individual population maxes out at 1,500. And at 1,500, this population cannot survive with 1,501. At that point, individuals are going to start to die faster than they can grow. So exponential growth would look like this. This would increase exponentially and then just continue. But that's not realistic. Maybe this is fish inside of a pond. And once the fish fill up all the space in the pond, they're not going to be able to keep having more baby fish and just keep growing in exponential growth. So if this pond can hold a maximum of 1,500 fish safely, then the growth is actually going to start to slow down. So at some point here, it's going to reach kind of an inflection point. And we see this very S-shaped curve. And this growth starts to slow down here, and then eventually the growth stops, and the population will sustain itself at 1,500. And this isn't always a straight line. It might go up and down and kind of oscillate around this point a little bit, where if it goes over 1,500, maybe there's more deaths. And when it comes under 1,500, we start to see a little bit more growth. And so it's going to keep itself close to its carrying capacity naturally just by the number of individuals that do well or don't do well. So here's a few examples of real data of two different populations. So let's look first here. This is a paramecium, so that's a protist. And protists, these guys live in pretty much fresh water. So if we have a protist that we're putting in a laboratory population, so we start with a few paramecium, and this is a lab, so we put them in an environment where they have some nutrients, they're going to grow, but it's also a lab, so it's confined space. So you can see here at the beginning it's got kind of an exponential look to it, and then eventually it starts to slow down and taper off here at about almost 900 paramecium. And notice that if I actually connect the dots, it doesn't taper perfectly. It's actually oscillating. So if it goes over its carrying capacity, it adjusts down. Once we're under the carrying capacity, we kind of can have more growth and go up. And so that's that oscillation, and I would expect this population to kind of do that for the rest of the time that it's in this lab environment. Here's an example of an overcorrection. So Daphnia is very fast growing. So it starts out very slow, and it actually overshoots its carrying capacity. And then it recorrects back down here, and then will eventually oscillate around this carrying capacity. So some populations will do this kind of overshoot where they were growing very quickly. And this almost looks like that exponential J curve. And then once we reach this high rate, these individuals start to die faster than they're being born, which is going to correct them back down to here, to where births equal deaths. And that's going to be when we're at our carrying capacity and the population is going to now stay the same size.